So what we're going to begin on today is now talk about how to do these mole-to-mole conversions. It is the same process, the same setup, but now, remember how I told you you need to write down the compound? Like every single time, don't just write down moles, but write down moles of what when you're doing your ratios? Like moles of iron, moles of nitrogen. Any kind of thing like that you need to write down. So what we're going to do is actually go over why you had to balance equations and why the molar ratio actually will help you out. This is basically how you convert between two different compounds. If they're mole to mole, then that's good. This is basically like kind of like switching continents. Like, you know how you go between different continents? Like if you were to go from US to Japan, you have to convert your money from dollars to yen. Okay. If you go to England or Europe, you're going to have to convert your dollars to pounds, things like that. It's still money, but it's just a different currency. So the same thing here. Moles is basically money, but you're just converting it to a different currency. And that's all this is. It's basically kind of switching continents. One reason why it all works out is that, and this is the one reason why you had to balance your equation, if you balance it properly, you can actually predict how many moles of something is actually going to combine together. And that's how we sum everything up. It makes things that are usually complicated science very easy. So if you look at this first part, since balanced chemical equations are ratios, we can use the coefficients to convert between two different compounds. Coefficients, remember, is equal to the molar ratio. So I told y'all, again, whenever we were going over the hydrates, that coefficient, that's your moles. So every time you've been balancing, you've been doing it in moles. You just haven't realized you've been doing it. So right here, it says how many moles of NO2 can be produced from 4.3 moles of N2O5? Well, first thing you got to do, you cannot solve that without balancing your equation. You have to balance it first. So if you take a look over here, you can actually kind of eyeball this one. It's a little bit split, but it works out. If you got two nitrogens here, what do you need over here? A 2. Well, if you have 2 here, that's 2 times 2, which is 4, plus 2, that's 6, okay? Well, there's the problem right here. That can't go into 6. So let's start back over. Why don't we double this guy? Because remember the odd numbers? We don't like odd numbers. Let's turn it to make it even. 2 times 5 now is what? 10, okay? So if we put a 2 here, 2 times 2, that's 4. Well, what do we got to put here to make that a 4? 2. So let's put a 4, sorry. You made me say it. So 2 times 2 is 4, so we need a 4 here. Well, 4 times 2, 8, plus 2, 10. So you have 10 here, 10 over here. And honestly, guys, if you end up with, if you forget your balancing, or if you have trouble, start back over. Look at odd numbers and try to, double it. Every time some people do that. So when we do that, we end up with 2, 4, 1. That's our ratios. That ratio's locked in. It's never going to change. So what is my ratio between N2O5 and NO2? Look at the red numbers. 2 to 4. Okay, what's my ratio between N2O5 and O2?
2 to 1.
2 to 1. Okay, what's my ratio between NO2 and O2?
4 to 1.
4 to 1. That's how you need to read it. And I'm telling you, you're only going to need 2 of the following. It depends what they ask you in the question. For example, right here, how many moles of NO2, okay, where's NO2? Can be produced from 4.3 moles of N2O5? Where's this one?
Right there.
Right there. What's your ratio between the two?
4 to 2.
4 to 2. That's your conversion ratio. In other words, 2 moles of N2O5 equals 4 moles of NO2. There's your ratio that you need to plug in to convert. And that's how we're going to actually go through and set it up. So let's actually break some of these down. See if you, and you're going to have to work these out, guys. It's just, it's a process. Now these are not so bad because we're just doing a mole-to-mole conversion. We are going to tie it in with what you're doing last time and actually put it, do a big long way conversion part. Okay, so right off the bat we said we have 2 moles of N2O5 are equal to 4 moles of NO2. Okay, so what did they give us in the question?
4.3 moles.
4.3 moles of what? Don't forget your compound. This is where the reason why I said start practicing with your compound in your conversion problem, so you can track it down and cancel it out. What we're going to do is not just cancel out moles, we're actually canceling out the compound. So it's kind of like keeping apples, apples, oranges, oranges. We're just converting between two types of fruit. So looking at this ratio, which one of these two have to go on bottom to cancel out the N2O5? The 2 moles of what?
N2O5.
So N2O5 will match with this one. If 2 moles of N2O5 go on bottom, then the 4 moles of N2O5, I'm sorry, NO2 go on top. And what that does is cancel out these guys. And you're left in moles of this. Yeah, basically you can reduce this fraction to 2 over 1, and yeah, you still get the right answer. But why do extra work, you know? So 4.3 times 4 divided by 2, what you going to get? 8.6. He is correct. Okay, so let's go through the next part. It says on number 2, it says how many moles of O2, okay, here's O2, can be produced from 4.3 moles of N2O5. There's your 2 ratios. If that helps, you might want to circle them while you do it. But if you do that, they like to do multiple questions with one reaction because they're lazy, or I'm lazy. So you got 4.3 moles of N2O5. So there we got a ratio. 2 moles of N2O5 will give us 1 mole of O2. Which one's got to go on bottom to get rid of N2O5? There you go. 2 moles N2O5. If that goes on bottom, then the other guy's got to go on top. Cancel out, cancel across. You're actually dividing by 2 technically on this one, and you get 2.15. And y'all are good. 5.5 moles. All right, so what's the ratio between here? We're going, I don't even read the question. N2O5, NO2. Where's your ratio at? 2 to 4. So which one has to go on bottom? Well, what matters what's here? 2 N2O5 and gives you 4 moles of NO2. Multiply across and divide, and you're done. And basically, you are ended up multiplying this one by 2, so you should have got 11 moles of NO2. Now, here's the thing. I will give you a reminder. Some people are like, why do you have a decimal? Okay, remember, a mole is not exactly a molecule, okay? However, ratios up here will always be whole numbers. That's the good news. Now, however, if you talk to a physical chemist, they will do it in decimals. And to me, that is incorrect. Because the way we always teach y'all in high school is always put whole numbers here for balancing. But they'll reduce it to a decimal, which does give you the same answer, but it's just kind of silly. Because you can't really have half a mole, or whatever. But just remember that a mole does not equal a molecule, and you'll be fine. All right, so now let's move on to this part. We're going to put everything together now. So we can't count atoms or molecules individually because they're too small and so many. So what do we use? What's the ratio? If we're going to molecules or atoms? Well, no, that's percent. Okay, step back a little bit. Molecules or atoms? What's the difference? How do you go between moles and molecules and atoms? 6.022 times 10 to the 23rd using Avogadro's number. Okay, so that's the ratio you're going to use there. We can't measure moles directly in lab because they're too, well, we don't have a tool that does that. We have a balance, which puts it in grams. But can we convert those grams into moles? Yes, we use our periodic table. Like, for example, if we were just measuring coal, which is just carbon, 1 mole of carbon would weigh 12.01 grams. Okay? If it's a compound like water, we add up the things and put them together, and that gives us a mole. And we just learned the next part, which is the middle creamy filling, which puts it all together. Okay? Using those reactions. We cannot convert between grams of reactants to atoms. Grams of reactants and products directly because how molecules interact with new compounds. There's too many of them, you can't count them all each individually and put them all together. So we use our molar ratio that we just used of a balanced chemical equation. Why should you write formulas correctly and balance them correctly? That's the reason why. If you do not do that, then you're never going to get this part right. So why did we do all the prediction and stuff like that? If you didn't crisscross or predict correctly, you can't balance correctly. If you can't balance correctly, you can't do this part. So they all build upon one another. Now we're going to mainly work with equations already given to you. You'll have to balance them, obviously, but then you just apply what you just have. So you are still balancing in this unit. Okay, But here's the problem. When we deal with gases, can you get the mass of a gas very easily? No. So you can't put gas, I don't know if you know this, you cannot blow up a balloon of helium and put it on the balance in the lab. One, it floats, but you can't, and then you're like, well, just turn the balance upside down, let it push up again. No, that's not how it works. You need gravity to actually kind of pull it down. So it's hard to get the mass of a gas. There's no definite shape nor definite volume. That's why the next unit is called gas laws. We got to do this whole unit based on gases. So what we do, we use something called STP, and no, it does not stand for Stone Temple Pilots or Standard something other petroleum. I know you see it all the time. Yeah, it's STP. It stands for Standard Temperature and Pressure. But anyway, basically they say if you have a mole of gas, so for example, gas is oxygen is diatomic, right? Okay, so you got two oxygens. 16 plus 16, what is that? 32. If you have 32 grams of oxygen, okay, that's 1 mole of gas. That 1 mole of gas is going to occupy 22.4 liters, which is actually a lot if you think about it. Because you got to think, gases fill up their whole container. And it's really kind of hard to measure them because they'll just fill up whatever the volume is inside there. Remember, there's a lot of space in between. So if we're wanting to do gases, we cannot do, if you look at the red guys up on your periodic table, we can't really go to, we don't really like to do it in grams. We like to take it and put it in liters because it's just easier to measure. And so basically when we deal with gases, we're going to use this ratio if we want to put it in a volume. And that only applies to gases. Okay, so don't think it applies to everything. Notice your mole is always going to be 1. The only time it's not going to be 1 is when you're dealing with an equation. That's a good way to look at it because some people start forgetting like, okay, well, what is the mole? Well, it's 1. So add this to your list of ratios. That is 4 ratios you're going to have to know. I am not going to have those on the test. You're going to have to know those. But by the time you get done with this unit and the practice worksheets I give you, you're going to know them by heart. Trust me. You already know the 6.022 times 23rd. That's the hard one. Just remember 22.4 liters. And that's standard. And I'll tell you how they figured it out, but I can't tell you till next unit. I know. It's one of those things. Okay, so there's this little chart right here. I'm going to give you one. Don't write this one down. I'm going to give you a better one. It's less complex. But anyway, if you look at this, you'll notice who is in the middle between every single conversion you're going to do? The mole. You can't cut them out. This whole unit is basically built around the mole. So notice going between particles, you're going to use Avogadro. Going between grams, you're going to use your periodic table to find the molar mass. And going between moles of gas, you're going to use that 22.4 liters. Just remember 22.4. It'll be fine. Okay, so we got back to our map, how to actually read it. So let me give you a sample question here. When NO2 is heated, it decomposes, and they give you this formula. So this is actually a question I'd give you, okay? So let's use that same formula we did earlier. How did we balance it again? 2, 4, 1. Okay, 2, 4, 1. So example 1, how many moles of N2O5 were used if 210 grams of NO2 were produced? Now here's the thing. What do you notice different from the last question? Are they saying mole to mole?
No.
No. They give you moles that you need to go to, but they give you grams of this stuff. So we got to convert that joker to moles before we can actually use it. Okay? So let's take that off to the side. I am going to switch through all this little stuff. Oh, by the way, before we actually move on, what is the 2 compounds that they're giving you? NO2 and N2O5. So we need that ratio. So what does it say? 2 moles for every 4. Let's keep that to the side. So we ain't got to keep coming back to this thing. You don't need anything else from your formula. You're done with that. As soon as you pull out your ratio, that's all you need. So just throw it to the side. That 1 mole of O2 ain't going to make a difference. If it's not asked in the question, it's not going to be involved. It's just that simple. Okay? So they said N2O5, you're going from 210 grams of NO2. Well, here's the problem. Oh, I'm sorry. Let me go back a little bit. Always write down where you're starting from and where you're going to. When you see how many or what is or any kind of thing like that, that's always going to be your ending factor. You need to end in units of moles of N2O5. So when you get done converting and everything, that should be your units. Not moles, not N2O5, but both. You're going to have 2 things. So we need to figure out a conversion route. So let's go back to our map. There you go. So you're starting where on the map? Well, what do they give you? Grams. Well, which one of these four is grams? Mass. So you're here. All right? So we need to go from here. The only pathway you can take, you can't go anywhere else except 2 moles. Does that make sense? You can't go here because there's no path. Okay? You can't go over her because there's no path. You have to follow the path. You've got to stay on the line. Okay? So they give you 210 grams of NO2. We need to go between this way. Well, there's your ratio of what you need to figure out. You need to figure out what 1 mole of NO2 weighs. So you need 1 nitrogen, 2 oxygens. Okay, is it 14.01 plus 16 plus 16?
46.01.
46.01. Look at y'all. Grams per mole. Now 46.01 grams are equal to 1 mole of NO2. That's what that means. If you haven't guessed yet, some of you are still writing down grams per mole as your final answer. You're never going to have that as your final answer when you're doing conversions because you're going to cancel out either the grams or the moles. You need to know that that is a ratio, that 46.01 grams is in 1 mole. Now we're in moles of NO2. Okay, now remember the question says how many moles of N2O5. All right, so to go between those two, we already wrote down our ratio. 4 moles of NO2 will give us 2 moles of N2O5. It doesn't matter which one I wrote first up here. But just note that's going to be your ratio. So which one of these two guys has to go on bottom to get rid of moles of NO2? 4 mole of NO2. That's why it's very essential that you write down a compound. If you just wrote down 2 mole to 4 mole, you're not going to know which compound's which. Well, be sure you label them. So 4 moles go down here. If that 4 mole went down here, that 2 moles got to go here. And yes, do you see why the process is an issue? But I use it every day in the lab. I would do this. We use this all the time. And okay, so what did the question ask? They wanted moles of N2O5. Is that your ending unit? Yup. So you multiply across. 210 times 1 is 210. 210 times 2. Okay, that's going to give you 420. So basically, I'm just going to put this on bottom here. Be sure you're plugging everything in your calculator. I like to do it all at once. But basically, this is what it would be if you're putting it in. 420 divided by that times each other. Notice I put it in parentheses. You should get that number down there, 2.28. All right, so let's look at this one. This one's actually kind of worked out on the board. So what you're going to have to end up doing, though, is I'm going to end up giving you questions. Now, that was a piece, that's just for explaining purposes. Let's actually look at a problem you'll see on your test. I'm going to give you this, and you're going to have to actually work out the whole stoichiometry. You're going to have to go back to reading your equations. Aluminum is an active metal. So aluminum, okay, is it bonded with anything? No. So you just write down aluminum, okay? Is an active metal when placed in hydrochloric acid, which y'all have already played with it. You should know what that is by now. That is going to be HCl. Produces, which is what symbol? The arrow. Hydrogen gas. H2. H2. Why H2? Diatomic. Okay. And aluminum chloride. Is that just AlCl? No. Crisscross. Aluminum has +3. Chlorine has -1. You should have AlCl3. This is why you need to do it. Because now you got to balance it. Every time you get the equation written, go ahead and balance it. And then they give you your stoichiometric ratios that you need. After we balance it, I'm just skipping ahead because you should know how to balance by now. If you would, you'd balance this side last. You'd actually try to figure out the ratio between the two. It works out in the end. How many grams of aluminum chloride can be produced when 3.45 grams of aluminum? Okay. So which one's that? And not talking about here, talking about the compound they just said. Where's that at on your equation? Right here. Okay. React with excess. Don't worry about the word excess. What does it mean when it says excess? I'm freaking out. I'm freaking out. It doesn't mean anything. It just means over the amount that you need. They had a limited amount of this. They had an excess amount of this. In other words, infinite amount that you would need to make it fully react. Okay? Which means don't worry about it. Okay? It's just there. What is hydrochloric acid? HCl. So the 2 ratio that you're going to need on this one is 2 moles of Al is going to give you 6 moles of HCl. And that's it. You don't need the other things. Once you found your ratio between mole to mole, you just get them, and then you're done with it. All right, so we pulled out that ratio, and that's what I go ahead and tell you to do. If they give you an equation, you're going to have to find that molar ratio, which should be easy peasy. Sometimes they go ahead and work it out for you. They're that nice. But on the test, you're not going to have that. All right, so what did they give you here? 3.45 grams. They want you to go to grams of aluminum chloride. All right, 4.3 grams of aluminum. Okay, how many grams? You're actually going from here to here. So there's your ratio. 2 to 2. Is that the same ratio as
1 to 1.
1 to 1? So you could just say 1 to 1 if you really wanted to. But I just say go ahead and plug them in. It'll work out all the same. Do realize, whenever you're going to grams and all that, you do not have to double the aluminums. You make up for that when you do the mole to mole ratio. So you don't have to worry about it. So they give you this in your equation of aluminum. And you're having to get to, what is the final unit? Grams of aluminum chloride. E. Okay, we got to get to this ending value. We don't know what that number is going to be, but that's what we're going to figure out. So you need, and I'm going to tell you, this is going to be a triple threat. This is how you're going to go between the two compounds, but you can't use that ratio right off the bat, can you? No, you can't, because that's in grams. So let's go to our map. Whee! Okay, so we're starting over on which one of these green dots? Mass. We got 3.5 grams of aluminum. We got to get to our moles, so we need the molar ratio between the two. We're here. We've converted over, and we got to cross the bridge. What does it say do? What's the ratio we got here? Every 2 moles of aluminum will give us 2 moles of that. So which one of these two got to go on bottom? It does matter which one.
2 moles of aluminum.
2 moles of aluminum. Because 1 mole of aluminum is right here. 2 mole of aluminum will give you 2 mole of aluminum chloride. But you're not done. Yeah, that'll give you aluminum chloride, but they want it in grams. All right, so we're in moles of aluminum chloride. There's only one thing left to do. We're now gone from here to the middle. Let me go ahead and do our ratio thing here. All right. So now we got to get to this guy. So we need between moles and mass. We do the same thing again, but we do it with a different compound. Notice over here we did the molar ratio of aluminum and just aluminum. They now want aluminum chloride. So we need 3 chlorines plus 1 aluminum. Let's cut to the chase.
133.
Ooh, look at that. All right, in other words, 133.33 grams of aluminum chloride equal 1 mole of aluminum chloride. Okay, now think very closely. Which one of these two has to go on bottom? Why? Because what's here? Moles of aluminum chloride. It wouldn't cancel out. Notice over here, moles was on top and grams was on bottom because you were converting between those two. Some people want to do the same thing here, and I'm like, no. Look at this guy. It all depends on who's in the upper left corner. And so that has to go on bottom. And again, if you master this conversion stuff, everything the rest of your life will be easy. All right, when you multiply across, how should you put this all in your calculator? Okay? 3.45 times 1 with parentheses times 2 times 133.33 close parentheses divided by open parentheses
And then the rest of it.
everything else. 26.98. If you want to be extra cautious, you just do everything like I do. But if you know 1 multiplying by 1, you probably can cut that part out. But basically, if you put that whole thing in your calculator, like you should, you will get that answer. If you can do everything in the calculator at once, you will get my answers on the test. Okay, so what do we do if we got a volume? So right off the bat, how many molecules are there in carbon monoxide container filled with 12.5 liters of gas? Let me ask you this question. Did they give you a formula? Not at all, right? Are you going to do a mole-to-mole conversion if they didn't give you a formula? They didn't even tell you a reaction. So you're not doing a mole-to-mole conversion here. You're kind of going back to what you were doing last week. You're using basically one side of the periodic table, or one side of that little map. So there is no reaction taking place. Therefore, no mole-to-mole conversion, okay? Will you be crossing the mole bridge? No. So here's the thing. That's what I mean by mole bridge. You're not going over here. They gave you, let's go back. So let's look at our question. They give us 12.5 liters of carbon monoxide, which is CO, okay? Honestly, it's not going to make much of a difference, but we got to keep it. We got to convert it. So they want you to go to molecules. Ooh. Right off the bat, you should know if you got molecules, what you're going to use. You're going to have to use your Avogadro. So 1 mole equals that 6.022 times 10 to the 23rd. Molecules. And however, this is the first liter problem I've ever given you. So that's why I'm doing this, so you have it actually in your notes. Well, where do you see volume given to you? So that's your start, right? Where over here do you see volume?
1 mole equals 22 liters.
So we're starting here, and we need to cross here to get to our moles. Notice we can't get to particles, which is the molecules. We can't get to there directly. We've got to go through mole and come back down. So we've got 2 conversions we're going to have to do. So there's our ratio. I'm not going to bother rewriting this down. So which one of these two have to go on bottom? And remember, you can leave off the STP. Y'all got it. So if that went on bottom, 1 mole goes on top. Boop, boop. And now we're in moles. So now we're here. We got to get down here. So what ratio do we use?
1022 times 10 to the 23rd.
So now which one of them has to go on bottom to get rid of the mole?
1 mole goes on bottom.
1 mole then gives us the 6.022 times 10 23rd. I'm not going to do it in a British accent anymore. All right, molecules. There. Molecules. All right, so basically the whole problem is this. 12.5 times 1, well obviously open parentheses, times 6.022 times 10 23rd, close parentheses, divided by, open parentheses, 22.4 liters. I'm sorry, let me just do 22.4 times 1. And that should get you an answer. You're not crossing the bridge here because there is no reaction. They just want you to go from here to here. So we got a ratio there. Now we got to go here. I turn it sideways. There's your other ratio. And you should end up with a big number like this.